Okay, so finally we saw that integration is nothing but perfect addition. Okay, so we have seen many type of addition, but if we go for kind of if our data is varying kind of every unit, then it is very fine. We can go for multiplication, addition, or other way of doing the calculation. But if our data is varying every moment, okay, so every moment in the sense the dependent variable has a kind of a function. So if it is a function, then function, like if I have independent variable as x and function is fx, then x can be 0.001 and it can be 8.0, it can be 6.955. So when we are looking for this much granularity, then we go for area approach. And now if we talk about the example, so example, we have shown a few examples, and working example we have shown the kind of like a person starts from a particular velocity and he reduces the velocity smoothly, kind of minutely, and reaches the distance and where he is kind of completely at rest. And in this kind of scenario, how we can calculate that if we know that what is the time he should reach a particular kind of distance. So he knows the distance and in how much time he would reach, he would kind of make the distance, and he is reducing his speed constantly, then at what speed he should start. So we showed that example through globe, and we know that how much distance, looking at the longitude and latitude, how much distance a globe would have to travel and how much time it should take. If we know that, then we can start with a velocity, and then with that velocity, if it gradually reduces the velocity and it reaches zero, then typically it will be rest the point where it has to reach. So that we saw. So integration is kind of a calculation in very fine granularity. Okay, now integration is not only limited to software or calculation. So I have a kind of inductor in my hand. Okay, so I tried. So inductor in a sense like it creates a magnetic field. When we apply a voltage across it, or we try to pass a current, if we apply a voltage across it through an inductor resistance circuit or inductor resistance capacitor circuit, whatsoever, then current would try to kind of flow through it as per the nature, but it will induce a magnetic field. Since it has so many coils, we can see that is rounded across a kind of core iron. So it will induce a magnetic field. If it induces a magnetic field, so it is kind of inertia, and means it has some strength. Okay, so it is not a kind of normal wire. So if it has a dense magnetic field, then it will oppose the rise of current. Okay, so that is the scenario. So if it is also more powerful, the inductor is more powerfully, it would oppose the rise of the current. So voltage across the inductor, okay, so initially it will kind of behave as open circuit. Capacitor behaves as the open circuit for voltage. This behaves as the open circuit for the current, and then there will be kind of high voltage across it, and then current would start slowly flowing. Means the inertia of this kind of device will be overpowered by the battery, and then at the end this magnetic field would not work and current will start flowing completely and voltage will drop. Okay, so if it is only guy that is connected, so voltage would drop in the sense that voltage across this in LR circuit also, it should be like there is a wire, so there should not be any voltage, and current should be maximum. So it will behave like a, so at the initially it will behave like open circuit for the current, and at the end it will behave like a closed circuit for the current. Okay, and if we talk about the voltage across this time to time, then it is the L, that is in Henry, it is measured as L, it's a unit of the inductor, L into di by dt. So at any time, what is the rate of change of the current? So if rate of change of the current is high, then voltage across it would be high, and rate of change of the current is low, then voltage across it would be low. So at the end, so there won't be any change in current because current is constant and full current is flowing. So voltage across it would be 0 as L into di by dt. So di by dt is no change in current, so it is 0. And in that case, the voltage across it is 0. So di by, but I is maximum. But problem with this we could not do, as the inductance is in kind of the micro or millihenry, and the tau, that is time constant. So time constant, if I say 5 into time constant, in that period it should reach, the current should reach its maximum. So that comes in millisecond. So that much, so for that we need a kind of function generator and oscilloscope to measure that. So we have kind of, we show that. So we have a kind of a very simple multimeter. So what we have done is we have taken a capacitor. Okay, so it is a capacitor, and this capacitor is from some company Maxcon, and it is written as 1000 microfarad, 15 volt. So it is operating voltage is 15 volt, and 1000 microfarad. It is a kind of so 1000 microfarad. It is kind of it has value, and 15 volt it operates. So that we are using now, and then as we talked that current is in inductor. So now we have inductor, capacitor, and inductor. So current across inductor kind of it is like so voltage. If I see the voltage across inductor, so beginning will be very high, and okay, so then it will kind of, it will make a exponential down, and then it will be kind of a flat slope, and it will reach to 0. So voltage across inductor, it starts from high, and it follows a kind of exponential curve, and then it reduces to 0. So beginning slope is high, and at the end slope is less. So same thing will simulate through capacitor, and current would be high at the beginning, the change in the current. So if you see the voltage across a capacitor, or if I say current across the current inside the capacitor, okay. So so current is nothing but dq by dt. So charge in capacitor is whatever charge it is storing. So capacitor stores the charge. So that is capacitance into voltage. So dq by dt, that is the current. So current equal to capacitance into dv by dt. So we can say that the current at any moment is equal to capacitance into dv by dt. So how much voltage is changing, that much is the current. So dq equal to c into v, dq by dt equal to c into dv by dt. So current equal to c into dv by dt. So if current is dependent upon the change in the voltage, so initially voltage change is high, so current will be high. At the end, voltage would establish itself, as the nature of capacitance. It's a kind of it's a charge storage device. So it will store charge up to its capacity, and then then voltage across it is. So initially it will oppose the voltage as per its inertia, we can say, or it is storing like inductance. I will talk about inertia, but the end it kind of giving in the sense that it stores some energy, and then it gives like a capacitor at the beginning. It has inertia, and then at the end it stores some energy, and then it gives it, and then voltage would reach to maximum. So that is the kind of so capacitor will see with the, now if I see I equal to C dV by dt, then it now if I try to calculate, then V, okay, so I equal to C dV by dt, so voltage will equal to kind of integration of the current. Now we'll come to integration finally. So if I see the voltage at any time, that will be integration of the I, okay. So now calculus integration comes into the picture. With that we'll calculate how much is the, with the formula that how much should be the voltage across the capacitor at any moment. Then we'll calculate the current, okay, and then we'll draw the graph. We will also calculate the capacitance. I don't think the way it is written and the quality of capacitor, it would be 1000 microfarad capacitor. Size is also very less. So with calculus, we will measure we will verify it is a good capacitor, because it should bring the curve as like exponential or logarithmic. And then if it is verified that it is a capacitor, nice working capacitor, then we will find its capacitance also. So that is the scenario. So that is the usage of integration. Okay. So we'll kind of we have everything in the integration, from software verification to hardware verification. Okay. So that is the story. So that we'll see. Okay. So we have taken a capacitor. This is a kind of 1000 microfarad capacitor it is, and we have taken one resistor. I think it should be visible. So a resistor is around 56 kilo ohm. I believe we can measure it. Okay, so first we'll see how much is voltage. So we have taken a battery source. So the voltage across battery source will measure. Okay, it is 2.6, and capacitor should be reset. No voltage, and we will measure the resistance. Okay, so it is 56 kilo ohm resistance. Okay, so we'll connect it. Okay, so we have finished the connection. So now I'll attach the battery, and then we'll see the change in current. Current should be, it should become 1 or 0. It would take some time because capacitor is powerful. It started with around 46. Okay, minus we are showing it is like ammeter is connected wrongly. Okay, so it has reached 11. We'll wait till it becomes kind of 1, take some time. Okay, so beginning was quick, and that is the kind of capacitance behavior, capacitor behavior. But reaching a kind of zero, it would really take time. Okay, so it reached 1, so I think we can stop it, and this is the kind of time duration it took. This is what we'll consider, or we'll wait till it will flip for 0. Okay, so I think it's enough. So we'll disconnect it, and we'll measure the voltage across. Okay, so it is flipping, so I think we are done. So we'll measure the voltage across the capacitor if it is really charged. So white is positive and blue is negative. Okay, it is really charged and it is discharging to 0.5352. Okay, this is the rate of discharge. Okay, so it will discharge slowly. Okay, so that is about the kind of a capacitor behavior. Okay, so as per the discussion now, we'll see for the integration we have seen for these shapes. Now we'll see the integration through measuring the capacitance. So that is the idea. Okay, so we'll add few slides. Okay, so we'll have a new lab session. So in lab session kind of okay, so as per the discussion now, we'll calculate the capacitance. So this is the capacitor, and we have very small resistor, that is 56K. and then we'll measure it. So how integration comes into the picture? Because capacitance is not resistor, so it's capacitance. Capacitor varies. So capacitance resistance, we can say the net reactance or net resistance of the capacitance, it varies over the time. So it is not a linear resistance. So it is variable and it varies exponentially. So we'll see like if this is a capacitor and charge across a capacitor that is stored at any time is C into Vt. So Vt is the voltage that is applied across the capacitor. And if C is the capacitance, that any moment how much charge is stored, at that moment whatever is the voltage into capacitance, that much charge is stored. Okay. Now if I see what is current, so current is nothing but dq by dt. If this is dq by dt, so the charge, okay, charge at any time, how much charge is stored, that is integration of the current. Okay. Okay, so how much charge stored at any point? So that is integration of the current. So if I try to write like this, Q equal to, so that will be integration of the current over the time, I dt. Okay, so we'll get integration sign from somewhere. Okay, so integration sign is a little funny. So this is the scenario here. Okay, it is not pasting at all. Okay, so this is the scenario here. And this is very important. So the charge stored at any moment. Okay, so charge stored at any moment is integration of I dt. So, or current at any moment is dq by dt, how much charge is getting stored. So, what is the diff in that? So, dq by dt. Okay. So, now if so all three vehicles, so if dq by dt is I, then I at any moment is C into dv by dt. Now, as we talked that if I kind of integration is nothing but calculating the area. If I have a curve whose equation is I and then I calculate the area, it becomes Q like that. So if this is the curve, we can see this yellow. This is the curve of I. So if I calculate this area, okay, if this is the curve of I, then integration, if I calculate the area, this area, so if we have a kind of close watch, then this area here it is less, slowly it is growing, okay, and area is maximum here, complete. This area curve, if I draw, that is Q. You can see area curve is growing. This is area curve, okay, and After a time it becomes stagnant. So this is Q. This is area curve. And this is the area. This is I curve. So if I know I curve, I calculate the area. That area is this curve. It starts from 0 and it proceeds like this. So this is integration. So if I have a kind of a voltage source, current, and it is a CR circuit or C circuit, then I have Q equal to CV. And if I have voltage source, then it is resistance voltage and capacitance voltage. If IT is the current flowing at any time T, then R into IT and QT by C. We proceed. And finally we come to a stage where dt equal to CR by dq. Okay. Now we come to another stage where dt by CR. Okay. Now we have CVS minus QT. Okay. So this is a kind of differential equation. So if I consider CVS minus QT as U, then dq equal to minus du. So finally we come to a equation where dt by CR equal to du by U. Now can we see there are two equations. One equation is dt. dt means dt is a variable. So here the constant is minus 1 by CR. 1 is missing here. So minus 1 by CR. So I am doing integration of minus 1 by CR dt over the time tt. So we are calculating area of a constant. Means time is constant. And here we are calculating area of the U. U is variable where means it is dependent upon capacitance. Voltage across the capacitance. If I see the U closely. So voltage across capacitance is variable and this is the variable. Now if I calculate the area of this, means I get the time and then calculate the area of this, then I get like this, and finally it comes to a kind of equation like voltage across the capacitor at any moment is like this, and T is at any time T CR. Okay, so this is the differential equation. Means we started with this and then like Ri. So Ri, I at any moment is dq by dt and qt by c anyway we have. Now we just shifting left and right. Okay. So dt, now we have two variables dt and dq. So left right we do and we reach here. Then we kind of, if I see this, okay, two variables there dt and dq. dq is changing. At every moment the charge storage is changing. T is changing. Every moment means moment is changing. And charge stored there is changing. That leads to this kind of equation. So there are two graphs, like we kept saying that now we have fx dx. So there are two fx, okay, that come in equal situation. So if there are two fx, then we integrate and finally we resolve it and it comes to logarithmic. Okay, so 1 by u integration is log ln, and we calculated many other integration like cos x, sin x, and x for k. If I calculate for 1 by u, 1 by x, it will lead to ln. Okay, if I differentiate ln, it will lead to 1 by u. And then finally ln minus means division, and then if I reverse the ln left side, it becomes exponential, and finally it comes to equation like this. If this is the equation, then current is, okay, if this is the equation, then current is differentiation, and it leads to equation like this. It equal to, okay, Vs by R e to the power Vs by R e to the power T into CR. Now, if time is 5 multiplied by CR, it leads to Vs by R 1 by 48. That is 0. Means this is called tau. CR is called tau or time constant. Time constant in the sense at 5 into CR, 5 into time constant. So can we see the graph? This is the graph is drawn based upon whatever we see, like 1000 microfarad capacitor we have taken, and then 2.6 volt battery we have taken. And if this is the scenario, we add the ammeter like this. If this is the scenario, then this would be the graph. So it starts from 0 and then around 210 it reaches the kind of a stagnant value. So we can say that 210 is the time when it becomes like 0. That time is nothing but 5 into time constant. So if I see this equation closely, okay, so if I keep growing the t, if it becomes 5c into r, then it is almost 0. So that is called time constant. Okay, it helps in finding the value of capacity. Anyways, so now we have done the experiment. Okay, so we have done the experiment, and this is the lab session, and we can see this capacitor is connected to resistor in series. Then in series ammeter is connected, so multimeter behaving like ammeter, knob is on microampere, and then ammeter is connected to battery, and then battery finally it is connected here. So in this circuit we went ahead and we calculated the current at in the reading, like initially it is fluctuating and then 46, 45, and these are the microampere that is appearing, and these are the time instance at which this microampere is appearing. And then like this, then we see that 11, so it started with around 46 microampere, and then it reaching 11 microampere at 1 minute. Okay, 46 to 11 in 1 minute, and then 0 in 210 seconds, that is 3 minutes 30 seconds. So that much delay it is taking. So now if I see the I formula, this is like this. So we can set up Vs is 2.6, 56 kilo ohm exponential minus t 1 into 56 kilo ohm and 1 milli kind of farad. So it comes to 1 into 56. Okay, so our calculation is, or now we know that 5 into RC is total time it takes to become current as 0. So 210. So capacitance, it is written 1000 microfarad, but we measure it as 750 micro. But anyways, this is the kind of code we have written in Python, and these are the readings so we have kind of used in a tuple, and then this is the theoretical Y, and then this is a practical Y, that is the kind of second element of that each tuple, and we plotted like this. So red color is the experimental one, what we got, and it is theoretical. So obviously it is different because we thought it is 1000. Okay, probably we can try with 750 and we see how close it is. We have the program. Okay, so here we have used 1. Now we'll use 7.50. Okay, and we'll try drawing it again. It is exactly same. It is exactly same. Okay, so our calculation is perfect. Okay, so integration is perfect. Means the way we thought about the integration, and this is the crucial point when we calculate the area, calculating the net charge, and then this is the graph we drew considering whatever is written on the kind of the capacitance. So capacitance, it is written as 1000 microfarad. As per the capacitance, this is what we got. But if I change it, then we get exactly like this. It is exactly like unbelievable. Okay, so I mean we can paste it. Okay, so we'll save it. Call like figure 3 and we'll import it. Can someone believe this? Okay, so I can point it that with this graph, a theoretical was made. Okay, so theoretical was made like theoretical 1000 microfarad. So theoretical was taken as 1000 microfarad. And I would rather say capacitance, capacitor. Okay, so when capacitance is 1, now in calculation now it is taken as 70 microfarad and they just coincide. So theoretically 750 and practically so means this is amazing. Okay, so 1000 as per the kind of written on the capacitor and what we believed it is 750 and it is same. Theoretical and practical is exactly same. Means unbelievable. Okay, so this is for integration. We use the concept of integration and we saw the capacitance characteristics and it is perfect. Okay, so this is the lab session. So probably we have finished the integration. So we started with kind of addition, simple addition, and simple addition becomes multiplication when it is too big, and simple addition in kind of in a triangular way. So it can be done like this. Okay, now simple addition, if I draw in a graph, so it is a rectangle. Okay, and then finally we came to three kind of like if I have simple addition, then it's a kind of different bar chart where multiplication cannot be applied. But if simple addition is constant over the time, then multiplication can apply. Otherwise, we have to calculate in this kind of addition, we have to calculate bar by bar. Okay, then we saw that multiplication becomes a integration. So sign we change. So integration only we sign we change, and lower limit, upper limit come in the while calculating the area. So integration is nothing but calculating the addition with a kind of solely through the area of the shape. So now if I have to find a region, that region is nothing but switching the sign, a lower limit and upper limit, and this is the equation of the dependent variable. So this is dependent is flat and its value is 5, so 5 dx. and then we move to triangle where equation is not constant, it is variable over the time. Time is varying, this equation is varying, both. So in that case, we saw that it leads to a formula. So we came to a conclusion that if k is 0, that is kind of a rectangle, or k is 1, then it is kind of a triangle. Then further we came to this formula. So, okay, so if I know the triangle formula, if I want a range between here to here only, not complete, then we have to place a range like this. Okay. Now we calculated so if I know the sine integration is cos, then this is nothing but just this area we calculate through integration. Then we calculate this area. So full area, if you calculate, it comes to 0 because sign is changing, it is negative, so person is coming back. Okay, so we lead to how integration formulas are built. It built upon smaller things, and we saw that how x to the power k become x to the power k plus 1 by k plus 1 in the integration. And then we found the integration of sin x, and it leads to minus cos x. So this is the way bigger thing they sit upon the smaller thing. Okay, then in the first experiment, what we saw as like a person is kind of moving, and then he is moving kind of in a way that it starts from a speed and it is decelerating constantly, it is reaching 0. So in this case, kind of if I know the total duration, how much it take, and if I know what is the distance is covering, what would be the initial speed? If I know the initial speed, then okay, so what would be its initial speed? Okay, so this would be its initial speed. If I know the initial speed, then I can calculate the distance covered at any moment. This leads to kind of we can kind of really locate a location in map with different velocity, with velocity rotating the globe in a fashion that initial velocity would be higher and it would reach to 0. In lab session 2, we saw finding the capacitance value or behavior of the capacitor, and that behavior of the capacitor we saw it is kind of follow the integration where any moment charge restored, net charge restored is integration of the I at that moment. And if I know the I equation, then I's area becomes the Q, that is the fundamental. Okay, then finally we came to equation of the capacitor, and then we took a 1000 microfarad capacitor and we had values, and then through values we drew a diagram, and our diagram is lacking. This is the actual diagram and this is our diagram. So with time constant we found out that capacitor is 750 only. If we are true, then we drew again, it is exactly same. Not bad. Yes. Integration is kind of a funny way of doing the addition. Like if I have speed and I want to know the total distance covered, then I have to calculate the area. If I have acceleration and I want to know the velocity, then I have to calculate the area. Means it is one term. So, like if I have distance I covered and I want to know the velocity, then I have to go for differentiation, means division. So, integration is, we can say that it's a smooth kind of addition. Like if I go for simple addition, then we don't expect gradual changes. Like within an hour, okay, So we calculate R by R. Like we saw that we started moving the globe, and it started with its velocity, and velocity started decreasing. Now at every moment velocity is different. Okay, so this is smooth kind of variation. Like if it is coast, if we are worrying every second how much is the distance covered, then next second how much is the distance covered, next second how much is the distance covered. If we care about that, not inside a second, again in millisecond and microsecond, only at the granularity of the unit, then we can go for addition. And if it is flat, then we can go for multiplication also. Okay, or we can go for funny way of addition. What is problem with integration? Integration is so nice, means just we need to calculate the area where the kind of the dependent variable may vary any moment. Okay, like we started the discussion with ball. Every hour I collect 7 balls or 5 balls. So at the end of hour, I see how many ball comes. We never think that if every hour we collect 5 balls, then how much is the collection at the end of 3.4 hours, 3.42 hours. We expect that the granularity is R by R. So this much smooth granularity, if we want, then we go for pure area. And area based addition, other name is calculus integration. So that we see. What is the problem with integration? The biggest problem is we have to find the function from independent to dependent. So independent to dependent, x to fx. Fx we need to find. Okay, that is not very easy. Like we have already shown that capacitor based. So there dq by dt is the current. Okay, so if I know the current, okay, if dq by dt is current, then integration of current is total charge. So if I have current graph, any moment if I take the area, then how much total charge on the capacitor is, that we can find. But how we can find fx? Okay, so the solution is a differential equation. So whatever the way we feel that how dependent and independent variable are kind of, they are correlated. Okay, if I know their relationships loosely, then we can bring in an equation and then we can find the fx. Okay, so probably in later videos we will see differential equations, and then we see that how we find the dependent variable, that is fx, from independent to dependent, from x to fx. Once we know fx, then next question is that for each entity in fx, we have to find their integration. Like if cos comes, then it is sine. If sine comes, then it is minus cos x. So that way, and how each entity are interrelated. If it is plus, then we can have separate integration. If it is multiplication, if it is division, then how they would be related to each other. So I don't think it would be very difficult to find it out. So we'll see that how differential equation, it helps us in generating the dependent variable, or handsomely we call it fx. So in differentiation, if I do differentiation of fx, it comes back to x. Okay. So integration of, if I integrate fx, okay, so if I have, if I have fx and then I integrate and I find gx, if I differentiate gx, then we come back to fx. So these are how this is how they are interrelated. If I have velocity and I do integration, then I get total distance. If I have acceleration, I do integration, I get velocity. If I have velocity, I do differentiation, I get the acceleration. If I have distance covered at each moment, how much distance covered, and if I do differentiation, then I get velocity. So, the reverse of addition is division. Like that, the reverse of integration is differentiation. But anyway, we'll see how we find the formula in integration so nicely we can get the area, and through area we get back what we want, and then we can kind of get our work done. Okay, so that we'll see.